Welcome back to the deep dive. So if you've been watching the energy transition, you know wind power is no longer the quirky cousin of the grid.
Not at all. It's the muscle
It
now.
is the muscle, but 2024 was it was defined by this wild contradiction. You had technical achievement on a massive scale, just running headlong into some really serious financial and geopolitical resistance.
That tension is exactly it. That's what our sources are highlighting. I mean, the headline figure on one hand is an absolute triumph.
Right.
You've got these massive macroeconomic headwinds. We're talking high interest rates, inflation, squeezing capital, all of it. And despite all that, the global wind industry hits a new annual installation record of 117 gigawatts.
117. That's just monumental growth. But here's the context that I think really matters for you, the listener. 90% of all new electricity generating capacity added globally in 2024 came from renewables. And wind is providing this huge share of that. We're past maturity now. This is industrial dominance.
What's fascinating, though, is that while 117 gigawatts was successfully connected to the grid, the manufacturing side was even more aggressive.
Oh, really?
Yeah, our data shows that the 29 active suppliers, they installed something like 127 gigawatts of mechanical capacity.
So there's a 10 gigawatt gap.
A 10 gigawatt gap.
Yeah.
And that gap is critical. It's the story of grid access delays, long construction cycles. It's the bottleneck.
And when we talk about who's building all this, you immediately run into a single overwhelming force.
China.
China. Staggering numbers. A 68.3% share of the world's new installed capacity in 2024. They now hold 46% of the entire global cumulative total.
Which is sitting at 520.6 gigawatts.
So that just begs the question, is this overwhelming capacity or is this a warning sign about dependence for the rest of the world?
It's both. I mean, it really is both, and that's the central theme for this deep dive. Our mission here is to really dissect what that scale means, to analyze the extreme technical race that's happening to hit these 15-megawatt units, and then
face the music on something the industry has kind of glossed over.
Exactly. The big one, wind turbine recycling.
Let's start with what you're calling the new cartography of wind power, because the map of where this energy is being built is, well, it's highly concentrated. But the ripples are starting to spread out.
The concentration is intense. I mean, the top 5 markets, that's China, the US, Brazil, Germany, and India, they accounted for 86% of all new capacity.
86%.
So if you're not a player in those big 5, you are fighting for a tiny slice of what's left.
But the map is starting to ripple, which is, encouraging. The sources point out some really interesting new players.
Yeah, like Kazakhstan and Uzbekistan, both of them crossed the 1 gigawatt cumulative capacity mark in 2024. That tells you wind is starting to accelerate well outside of its traditional strongholds.
But on the flip side, you have to talk about the headwinds that are hitting the established regions.
For sure. Annual installations in Europe and North America actually dropped. And this isn't a failure of demand. It's a failure of infrastructure and, well, bureaucracy.
So it's the permits, the grid not being able to keep up.
Exactly. The complex permitting, the grid lag, and all that financial stress that's hitting the big offshore projects.
And if we split it between land and sea, the numbers tell a story of 2 totally different markets, right? Onshore, the workhorse, installed 109 gigawatts. That's steady growth.
About 3.1%. Very solid.
But offshore installed only 8 gigawatts. A massive 27.5% decline.
Yeah.
Why the huge drop-off in offshore when the need is so high?
Well, that offshore decline, that leads us directly into the competitive arena, which we're calling the competitive tilt.
Okay.
Because that drop-off is overwhelmingly due to Western megaprojects getting canceled or delayed, financial stress. And this is all happening at the exact moment the global manufacturing balance is just completely fractured.
The speed of it is what gets me. I mean, Western manufacturers, just 5 years ago, they held something like 60% of the market.
And now, less than 20. The sources are crystal clear. 2024 was the year the balance just broke.
So who's on top?
The rankings for mechanical installation volume are... They're astonishing. For the first time ever, Chinese OEMs, original equipment manufacturers, they swept the entire top 4 spots.
The whole top 4, leaving the Western giants behind.
Completely.
So let's talk about number 1, Goldwind. Nearly 20 gigawatts installed, 3rd year in a row at the top. And they made this radical pivot in their tech.
They did. They moved away from direct drive turbines and went all in on medium-speed hybrid technology.
Why was that specific engineering choice so important for winning the cost war?
Because it wasn't just marketing. It was a fundamental engineering choice that slashed their manufacturing costs and, crucially, made upkeep so much simpler in the field.
So direct drive systems are just too complex, too heavy.
Way too complex, way too heavy. Goldwyn's strategy, shifting 89% of their installs to hybrid, was all about finding that sweet spot. It's lighter, it's cheaper to make, and it balances power density with maintenance far better than pure direct drive. They optimize for the balance sheet and for the maintenance crew.
And meanwhile, the traditional Western giant, Vestas, drops to number 5. But there's a really important nuance there, isn't there?
A huge one. Vestas is still the most globalized OEM. Outside of China, they still hold 30% of the market share.
Which shows that brand trust, the service networks,
Yeah.
that stuff still matters in complex international markets.
It matters a lot. And you can't overlook Siemens Gamesa or SGRE. They had a bit of a king's return, retaking the #1 spot globally for offshore wind suppliers, even with all that financial turbulence.
So that really defines this two-tiered market you mentioned. You have the Chinese OEMs who are just completely dominant at home. 94% of their capacity is domestic.
But those domestic price wars are so intense that they have to expand internationally just to survive.
And their strategy there is very targeted.
Extremely. They're going after price-sensitive regions. Asia is over half of their overseas installs. Then you have Africa, South America. The price advantage is undeniable. We're talking 25 to 32% cheaper than Western models.
But the high-barrier markets, Europe, North America, they're still tough to crack. Why can't they just go in and undercut the price there?
Two big reasons. One is local content requirements, mandates to use locally made parts. And two, there are very serious concerns over bankability.
Bankability, so that's the long-term reliability, the financing risk.
Precisely. Will this new equipment last 25 years? Can you get a multi-billion-dollar loan against it? That's the question. Which leads us nicely to the technical frontier, what everyone is fighting to build. Bigger, smarter, and floating turbines.
The industry mantra is large scale, high tower, long blade. And the global average capacity for new units hit nearly 5,500 kilowatts, a 9% jump in just 1 year.
And for onshore, we officially crossed the 5-megawatt threshold for average turbine capacity. The tech making that happen is that medium-speed drive we talked about. It's booming up to almost 30% market share now.
And the blades, they're just getting enormous. Rotors over 180 meters in diameter are now mainstream. That's almost 60% of the new market. You can't build something that big out of the old materials. It would be too heavy to even spin.
And that's where material science comes in. Carbon fiber. It's expensive, it's complex, but its use is steadily increasing, especially for those monster turbines over 10 megawatts. You just need its strength and lightness to manage the weight.
Okay, so let's go back to that offshore paradox. Low installations in 2024, but a huge surge is supposedly coming.
Right, an installation trough, but an auction peak. Over 56 gigawatts of capacity were awarded globally. It's a massive pipeline, and it signals a huge surge starting around 2027.
And the size of those new turbines is just mind-boggling.
The average offshore turbine installed in 2024 was about 9.8 megawatts. But the new standard for orders in Europe and China is now the 15-megawatt class.
15 megawatts. That's nearly double the average size of what's already out there.
And to get to 15 megawatts and beyond, you have to go into deeper waters. Which brings us to floating offshore wind, or FOW.
Which is moving fast from just a concept to actual demonstrations. About 278 megawatts connected globally now. So how do you actually do that? How do you stabilize a massive turbine miles out at sea without an anchor to the seabed?
There are basically 3 main platform types. The most common is the semi-submersible. Think of an offshore oil rig. It uses these big buoyant columns, and you can assemble most of it in port.
Okay. Then you have the spar platform.
The spar is the easiest to visualize. Imagine a giant submerged pencil standing on its tip. It's a very deep cylinder that gives you incredible stability, but you need really deep water just to install it.
And the last one, the tension leg platform, or TLP, sounds like the most complex.
It is, but it also gives you the best performance. It uses these tight vertical mooring lines like specialized steel cables anchored to the seabed. It nearly eliminates any vertical movement, which is amazing in rough seas. But yeah, the installation is a huge undertaking.
And all these marvels are incredibly expensive. Which brings us to the financial reality check. The bottom line and macroeconomic headwinds. We have to ground this in LCOE.
The levelized cost of energy.
Right. Explain that simply.
It's just the total lifetime cost of producing 1 unit of electricity, usually a megawatt hour. It includes everything, the capital, the financing, the operations, the decommissioning.
And the numbers.
The efficiency of onshore is clear. Mid-resource onshore wind is around $42 per megawatt hour. Fixed bottom offshore is $117, and floating, still in its early days, is the highest at $181.
And the key factor here is the interest rate crunch. Wind is all about huge upfront investment.
Exactly. It's a capital-intensive industry. So the LCOE calculation is heavily dependent on the discount rate, which is basically the cost of borrowing money.
When central banks raise rates, that number goes up and the whole project can fall apart.
It's like adding 400 basis points of extra mortgage interest to a multi-billion-dollar project. The sources confirm that's exactly why European developers were walking away from bids in 2024. The math just stopped working.
And on top of that, you have serious supply chain choke points, especially as you get past that 10-megawatt mark.
Yeah, it's not just steel. It's the specialized high-torque components.
The gearboxes.
Gearboxes, exactly. The top 5 players control 80% of that market. And the main bearings have to handle just extreme loads for the turbine's entire life.
And then there's the political risk baked into the materials. Medium speed and direct drive turbines need rare earth magnets, neodymium, dysprosium.
And for U.S. offshore expansion especially, being dependent on imports for those critical materials is a major geopolitical risk.
A risk that's compounded by trade policy. Protectionism.
It's a reality. The U.S. proposal for tariffs, 10% on Chinese goods, 25% on Canadian and Mexican goods. It sends a clear signal. Energy is now an economic weapon.
What's the bottom line impact of that on the energy transition?
Well, the analysis shows a general 25% tariff could increase U.S. onshore project costs by 7%. That directly raises the LCOE by 7%. So while you're trying to build a domestic industry, you are definitely slowing down deployment in the short term.
Okay, so let's pivot to the next decade. If we're hitting physical and financial limits, the next revolution has to be digital, right? It has to be in operations and maintenance, or O&M.
It has to be. The shift from passive to predictive maintenance is essential, especially out in the deep sea. And AI algorithms are proving incredibly effective at this.
What kind of performance gains are we actually seeing from AI?
It's boosting short-term wind forecasting by about 10 to 15%. But more importantly, by spotting those tiny early signs of failure, a micro-vibration in a bearing AI is reducing unplanned downtime by 20 to 30%.
And unplanned downtime is the profit killer.
It is the biggest killer.
Let's dig into that digitalization more, because the sources mention wake steering. This sounds like a genuinely high-tech application of AI.
Wake steering is an advanced technique where an AI coordinates the yaw angle. That's the rotation of the upstream turbines.
So it's steering the wind.
In a way, yes. It's steering the wake. They guide the airflow to reduce the turbulence hitting the turbines downstream.
So it's like a digital choreographer for the whole wind farm, making them dance around each other's bad air.
That's a perfect way to put it. And that single, clever digital trick can increase the total farm output by 2 to 5%. That's free energy from assets you already own.
And the physical inspections are going robotic, too. Drones are becoming standard.
Autonomous drones using AI visual analysis to spot tiny cracks or corrosion on blades way faster and more accurately than a human ever could.
But we can't talk about the long term without tackling that big sustainability gap. The recycling challenge.
The Achilles heel.
Yeah. 90% of a turbine.
Yeah.
The steel, the copper, it's easy to recycle. But the other 10%, the composite blades. That's the problem.
This is the recycling last mile problem. And the scale of this it's enormous. And it's approaching fast.
How big are we talking?
Europe alone is expecting 60,000 tons of blade waste a year by 2025. And that's predicted to spike to 800,000 tons a year by 2050. That is a ticking clock for a supposedly green industry.
So what are the solutions now? Why aren't they good enough?
Right now, they're pretty low value. You have cement co-processing, where you basically just crush up the blades and burn them in a cement kiln.
Okay.
Or you have physical reuse, which is kind of cool, turning old blades into bridges or street furniture. But that doesn't recover the valuable material inside.
The real game changer would be high-value recovery.
Yes. This is cutting-edge stuff. Using processes like pyrolysis to chemically break down the composite and extract those high-quality long fibers.
So you could reuse them in new high-performance products, maybe even new blades.
That's the dream. That's the true circular economy. We have to get the cost of that process way, way down for it to be scalable.
And policy is finally catching up to this.
Yeah.
The EU is mandating material passports and recycling commitments for new projects.
which is the kind of accountability you need to close this loop before the crisis really hits.
So when you put it all together, the tech leaps, the financial squeeze, the geopolitics, what does it all mean for the strategic future of wind?
I think it means we have a very clear two-track global market.
The Chinese track, which is all about overwhelming scale, low cost, and speed, and then the Western track, focused on high-value digital services and, protecting those core domestic markets.
And I think the most important implication for you, the listener, is this. Geopolitics have fundamentally changed how governments look at wind power.
It's not just about the cheapest electron anymore.
Not at all. Energy security, national sovereignty, those are now often prioritized above pure levelized cost of energy. Wind equipment is now strategic national infrastructure. It's a total revaluation of what energy value even means.
Which leads us to the final strategic question for the next decade. The sources note that just building bigger, pushing past 15 megawatts, you run into these nonlinear cost increases. Materials, logistics, stress.
You're hitting the limits of physics and logistics at the same time. So will the future of wind be defined by some physics-defying 20-megawatt turbine?
Or will it be defined by the digital revolution, where things like AI and wake steering unlock way more efficiency from the 10 or 15 megawatt turbines we already know how to build?
A fascinating convergence, isn't it? Hardware limits versus software solutions.
Something to consider as you watch this monumental shift unfold. That's it for this deep dive. We'll see you next time.